MAP4C 5.2 rates of change. Recall that a rate is a comparison between two variables. It's a ratio or a fraction comparing two variables. As we're analyzing the change between two variables, we can look at two instances, 2 points, and the average rate of change, regardless of how it's fluctuating in between those 2 points, is the direct line between those 2 points, which we can calculate using the slope formula. The average rate of change between 2 points is the slope of the line segment joining the points. M is equal to rise over run, which the point slope form is y2 minus y1, which is just the change in height, that's the rise, divided by x2 minus x1, which is the run or horizontal displacement. So in a table of values, if you're looking for the average rate of change between two particular ordered pairs, so at time 0 the height was 2,000 meters, and at time 4 minutes we had 1,400 meters. So to find the average rate of change between these two points, we can use the slope formula. Remember that x1, y1 is just referring to the first point. If you were to picture this as a graph, it would be the point on the left, and the second point, which is x2, y2, is like the second point on the right. So the slope, which is y2 minus y1, the change in height, and the change in height is 1,400 minus 2,000, versus the change in time, which is 4 minus 0. When we evaluate this, this is not as helpful as having the unit rate. This is just a rate. This is minus 600 meters for every 4 minutes. But it's useful to use the unit rate, which is the amount for one of the denominators. So think of it as we can divide this fraction, and we end up with the rate for 1. This is dividing the top by 4, dividing the bottom by 4. And then this is more useful. Minus 150 meters for every 1 minute. So we can determine the average rate of change, or approximate for a longer duration, using this base rate, the unit rate. Now, as a graph, using point 1 on the left, as we said, is 200, 400 in this case, and the point on the right, that's 400, 700, then we can use our slope formula. And the change in height, which is 700 minus 400, so divided by the horizontal displacement. So we have 400 for x2 and 200 for x1. So that difference is 200. Be careful to be aware of what your x scale is and what your y scale is. The x scale refers to, for one grid space, how many units does that represent? And in this case, it is 100. So it's a 1 to 100 scale. And on the y-axis, it's a 1 to 100 scale as well. So the slope formula rise over run is not helpful when it's not a one-to-one relationship, and this point slope form is going to be accurate in describing this increment for horizontal change and vertical change, rise and run. Now, the advantage of graphs is that you can notice long-term trends, but we lose a little bit of precision. Sometimes it can be challenging to figure out exactly what the height is, for example, at 300 kilometers. It's tough to approximate. It's easiest to identify points that go through these grid lines. You can see the blue grid. When you can clearly identify points, that is when it is easiest to use a graph to determine the rate of change, or the slope. So in this case, it's much more helpful to understand that for every kilometer that you travel, you're charged $1.50, as opposed to a rate of $300 for 200. Next, identifying rates of change in a table or graph. So if the rate of change is 0, the first differences will be equal to 0. And think of the table with the values in the height will always be the same if the height is not changing. So subtracting those values, anything minus itself is equal to 0, we'd end up with a graph that looks like this, and those differences in height is 0. Next, constant. If the first differences are equal, we have to consider the following. The x intervals are equal. Here we see a difference of 10 between each of the x values, so we're using a regular increment for our run, as you see here in the graph. And the reaction distances are y value. We can see that there's a difference of 2. Now what they've done in this table is expressed it as a rate, where we have the change in height, so that's the difference in y values, 2 minus 0, divided by the difference in the run, 10 minus 0. So this ensures that we end up with a constant rate, and we see that the rate in each case is 0.2. Now this makes sense because if we were to compare our rise over run, it's always going to be equal to the same ratio. So even if you were to look at maybe this first and last value, which would be a rise of from the origin to 50, 10, the change in height is 50. Sorry, the change in height is 10, and the run is 50. So 10 divided by 50, that is equal to 0.2 when calculated, and that's consistent. So it doesn't matter the interval. If it's a linear relation, the first differences will be equal, or the rate of change will be constant. Lastly, changing. If the first differences are changing, so meaning that we subtract adjacent values for both the x variable and the y variable, as you see here, expressed as a rate of change, the result when calculating the rate of change is different. And if you have a rate of change that is not always the same, remember that these represent the slope of the line between, it's the slope of the line segment between points. And we're seeing that they are different at each point. As you can see, the slope is gradually increasing, and then it begins to rapidly increase. So this is nonlinear for that reason.